Hi there, welcome to the Grand Canyon. I'm Steve Reynolds, President's Professor in the School of Earth and Space Exploration at Arizona State University. And we wanted to give you a little tour of the Grand Canyon since not everybody can travel these days. The Grand Canyon is one of the best places in the world, if not the best place in the world, to look at geology, to look at landscapes, to see how the different rock types are expressed differently in different parts of the landscape, and also to try to look at a little bit of geologic history and to figure out how do we figure out the sequence of events, what kinds of changes happened here, for example, changes in environment, and when did all this occur? In thinking about the geology of the Grand Canyon, we always start with the sequence of rock layers. So this view, we're at Mojave Point, which is in the western part of the Grand Canyon along the road between the Grand Canyon Village and Hermit's Rest, so west of the main part of the park. And this has a really nice exposure of pretty much most of the rocks we'll see. There's one package in here that we don't get a good look at that we'll look at later. But in here, so what you can see is you can see the Colorado River. Down in the bottom of the canyon, there are some dark rocks that don't have a lot of obvious layers from right here. Those rocks are Precambrian metamorphic and granitic rocks. They're the oldest rocks in the park. They're the oldest rocks in the region as well. They're approximately 1.7 or so billion years old. Some rocks are a little older, some rocks are younger than that in that package. But that sequence of rocks in what's called the inner gorge, those are the oldest rocks in the canyon. Sitting on top of the basement rocks is a ledge of sandstone down just above the river, and that is called the Tepete Sandstone. It's named for a place in the Grand Canyon. Geologists name formations after places, not other people or themselves. And that rock is about 550 million years old. It's Cambrian. And so there's a big difference in the age between the basement rocks versus that first sandstone. The boundary of the base of the sandstone sitting on the crystalline rocks is called the Great Unconformity. It's a place where you made those lower rocks, and we'll describe that a little bit later. You made those lower rocks, you uplifted them, you eroded everything off, and then much later, the seas came in and deposited this first sandstone. That sandstone is a shoreline facies, so it's got beaches and rivers close to the shoreline and things like that. And so that's the first advance of the seas in here. So in thinking about the Great Unconformity, you say, what happened during that time period? What we know is you made the lower rocks, and you made those at depth. Those were like 20 kilometers deep. And so those rocks had to be uplifted to the surface, and you had to erode 20 kilometers of rocks off the top. And so that happened. And then you say, did nothing else happen in here between the Cambrian sandstone, the Tepete Sandstone, and the underlying crystalline rocks? And the question is a good one, but the answer is complicated. Lots of stuff happened here. You had uplift. There's another sequence of rocks that's locally present along that boundary, and those rocks got deposited and tilted during that same time period represented by this unconformity. So you might look at the contact between the Cambrian sandstone and the underlying crystalline rocks and think that, well, all that happened in here was erosion. But in the other parts of the canyon further east, there's a whole package of rocks that was deposited and tilted and eroded during the time period that's represented now by just that great unconformity. So when you look at something like that, it's not like nothing else happened anywhere even close by. It's just right here, there's no record of what happened except there was uplift and erosion. the river carved down, and then the tributaries of the canyon widen the canyon by eroding sideways from the main Colorado. The other thing that widens the canyon in here is that you have gravity working on all these steep cliffs, and so large pieces fall off the cliffs, and that ends up eating the cliff back as well. When we see a sequence of sedimentary rocks like this with layers, it's important to think that the layers represent either an event, like a single storm that deposits a layer of sand, or a layer represents a time when the environment was within a certain set of parameters. For example, maybe it was sand dunes, or maybe it was a series of rivers. And the boundaries between layers are therefore changes in the type of the environment that was around at the time. So for example, you might have a limestone layer that was deposited in coral reefs, and then it's got some other rocks on top of it that represent river deposits. And so at that point, the land had been uplifted or the sea had dropped down, and so you went from a marine environment into one that had rivers on land. Within the Paleozoic rocks, at the base, there are three units that are very much related to one another. The basal sandstone is the Cambrian Tapeats sandstone, 550 million years ago, thereabouts. And that's a shoreline facies where the seas first came in. Sitting on top of that, and expressed as a slope, is a unit called the Bright Angel Shale. And it's mostly kind of green and gray, not very well exposed because it's a shale. It's very fine-grained rocks, and so they're not very strong. And then sitting on top of that is a kind of series of little ledges that are a little bit yellowish again, a little bit greenish, depending on where you are, and that's the Muav limestone. And so those three rocks, the Tapeats, the Bright Angel, and the Muav, essentially represent the seas coming in, what geologists call a transgression. The first time that the seas came onto the land, you deposited the beach sand. And then when the seas had moved farther inland, then you're in kind of a shallow, muddy sea, and so you deposit the Bright Angel, and then eventually the shoreline's far enough away that there's less land-derived material coming in, and it's clear enough water that you can have marine organisms that build the limestones. Sitting on top of the highest of those three Cambrian units, in most of the canyon, is a cliffy limestone called the Redwall limestone. And that forms these nice gray cliffs. It's called the Redwall. It's a gray limestone, but it's called the Redwall because the overlying red rocks of the Supai group contribute a lot of iron oxides that run down the face, and so they stain that gray limestone into a kind of a reddish color, and that's how it got the name Redwall. Locally in some parts of the Grand Canyon, between the Redwall and the underlying Muav limestone, there's another unit called the Devonian Temple Butte Formation, named after Temple Butte. But it fills channels in general in this part of the canyon. And so as you look at most of these walls, you don't see that rock. But in some places, like if you go up some of the side canyons, you'll see a little place where there's a little wedge of a little lens of something else that's between these two rock units. And that's because you had erosion, and then you deposited a little bit of this stuff, and then you had the next unit deposited on top. So the Muav gets carved into little channels, the Devonian Temple Butte Formation fills those channels, and then the Redwall comes over the top. On top of the Redwall is a series of red units called the Supai group, and the boundary between those two rocks is a major erosion event. If you walk along that contact down along the trails in the Grand Canyon, the limestone has been dissolved and there's a whole bunch of reddish soil in there. We typically call that stuff terra rosa. It's typical of a tropical soil derived from limestones. And so there was a major event in here that deposited that red soil derived from the underlying Redwall. But the other thing it did, it carved caverns and sinkholes and things like that in the top of the Redwall limestone. So that surface, but at the top of the Redwall below the Supai group, is a karst surface. We call it a paleokarst because it's old. And it's really well expressed in a number of places. because of that karst event, you had a lot of groundwater go into the Redwall limestone and dissolve it. So you made a whole series of caves. And so those caves are exposed around different parts of the Grand Canyon. The other thing that happened is some of those caves collapsed, the roof collapsed, and so the rocks above it were no longer supported. And so that collapse kind of ate its way up to the surface, and you have these columnar funnel-shaped features called breccia pipes, because they're all composed of angular pieces of rock, which geologists call breccia. And so there are a number of breccia pipes in the vicinity, in the Grand Canyon, exposed in the walls of the Grand Canyon, and exposed on the surface around us, the Kaibab Plateau. Some of those breccia pipes actually had fluids go through them that deposited materials that are valuable. For example, here in the Grand Canyon Park, there's a mine called the Orphan Lode, and it was actually a site where they mined copper at the start. And then later in the 1940s, we decided we needed uranium, and they discovered that the Orphan Lode also had uranium in it, and so they mined it for uranium. Further west, there are a couple mines where, again, in breccia pipes where they've mined them strictly for uranium. So these masses of broken rock were nice conduits where the water could come up and deposit whatever that water was carrying, whether it was copper or uranium. The reddish rocks in the middle of the Grand Canyon is called the Supai Group, and it's a whole series of ledge-forming sandstones and slope-forming finer-grained rocks, siltstones, mudstones, shales. It's got a few other things in it, like it's got some gypsum in it here and there from water evaporating, but it's mostly just a whole series of alternating shales and siltstones. It's very rhythmic. I mean, there are a whole lot of ledges in here where you've changed back and forth between depositing fine-grained rocks like siltstone versus sandstone. And that rock was deposited during the time when there was glaciation going on, and so the sea levels were going up and down as the glaciers melted and reformed. And so as sea levels went down, you make one kind of rock, and as sea levels come up, you make another kind of rock. As you take this rock further to the west, it has limestones in it. And so the limestones come in at times when the sea level was high, and the seas were able to come into the western part of the canyon and deposit those limestones. There's some limestones in here, but they're pretty inconspicuous. If you look at the Supai, there's an interesting story that's developed about where the sand in that rock came from. For years, decades, we talked about those red rocks as coming from a local set of mountain ranges in the western U.S. called the Ancestral Rockies, like around, west of Denver, up in southeastern Utah, northern Arizona had one of these mountain ranges. And so we always thought that sediment basically came off those mountain ranges, off the Ancestral Rockies, so locally derived stuff. The red rocks in the middle of the canyon, called the Supai Group, illustrate an interesting way about how science works. For decades, many decades, 5 decades probably, 4 decades, we thought that the red sediment in those rocks, the sand grains and things like that, came from a series of mountains called the Ancestral Rockies that are in Colorado, Utah, northern Arizona, and northern New Mexico. And so for years, we taught students, hey, all that stuff came from the Ancestral Rockies. But then somebody came in with a new technique, detrital zircons, and they take the samples of those rocks, they grind them up, they separate the zircons out, and then they probe the zircons with a laser, and they can determine the age of each individual zircon grain or each individual spot within a zircon grain. When they did that, what they found is that these rocks had ages that were 1 billion years old. Well, we know a lot about the age of the crystalline rocks in the Southwest, and they're not 1 billion years old. They're 1.7, 1.4. And so you say, well, where did all this sediment come from that has 1 billion-year-old zircons? It turns out the Appalachian Mountains has a ton of those zircons. That event in the Appalachians is called the Grenville event. And that series of rocks has a lot of zircons in it. And so the conclusion from these first zircon studies in the Grand Canyon were that this stuff, some of it came from the ancestral Rockies, but a lot of it came from the Appalachians. And so this was a case where there was a consensus, and it totally got blown away by a new method that made us look at those rocks in a very different way. The same group that did those zircons did them on the Coconino sandstone, one of the higher layers, and that mostly has Appalachian zircons. And so what you get from that story is that the Appalachians were essentially the continental divide, part of a big mega continent, and you eroded material off the west side of the Appalachians, and that material came in streams all the way to Utah and Arizona, and then probably got reworked by wind and longshore currents and streams and other things and got moved around. But essentially that material came from the Appalachians, and a lot of it ended up in the middle of the Grand Canyon in the rocks that we call the Supai. On top of the Supai is a unit called the Hermit Formation. And it's mostly covered because it's another really fine-grained material that's weak, easily eroded. And so it forms a slope, and it's got a big cliff of sandstone on top of it. And so the sandstone contributes all these particles, these big fragments, blocks, and they essentially cover up the Hermit in most places. But as you look around the canyon, you can see places where those red rocks on top of the Supai and below the big sandstone cliff peek out. And initially, the Hermit was also part of the Supai, the first people who worked in here, but then later somebody pulled it out. I personally think that was a mistake to have pulled it out, but that's what happened. And so now you have this whole series of red rocks, including the Supai and the Hermit, sandwiched between a lower limestone and the next unit on top. The Hermit has a very famous collection of land plants, and so we have a pretty good idea of when that rock was deposited, and it was also deposited in kind of the middle to late part of the Middle Permian. Sitting on top of the Hermit is one of the big cliff formers in the Grand Canyon. It's called the Coconino Sandstone. It's a tan to brown to tannish brown cliff, and it's the biggest impediment for getting in and out of the Grand Canyon because it makes a cliff like that. And so the trails into the Grand Canyon are places where for some reason that rock is not quite so strong and not so cliffy, like when there's a fault that's come through and has broken it up. And so it was easier to erode it, and so it wasn't a steep cliff, it was just a slope. The Coconino has beautiful crossbeds. Crossbeds are things where you have the beds like this, and between them you have these curved beds at an angle, or planar beds at an angle, but we call those crossbeds, and those indicate which way the current was flowing or which way the winds were blowing that deposited that material. The Coconino has really big crossbeds that are really curved, and that is a diagnostic signature of being deposited by the wind. So when the Coconino was deposited, this was a big sand desert like the Sahara. On top of the Coconino, there are two units that are kind of related, and so some geologists just kind of lump those together. The one right above the Coconino is called the Toroweap, and it's a series of ledges and slopes. And then the top unit is the Kaibab limestone. That's one of the dominant rock types in the Grand Canyon. It forms the rim of the canyon here in the south rim and in the north rim. And it's a series of really nicely defined layers in a gray limestone that sometimes has yellowish tint, sometimes has a little bit of pinkish tint, sometimes has a brown kind of character. And so as you look out along the canyon, the top of everything that you see is the Kaibab limestone. It's also Permian in age, about the same age pretty much as the Coconino and as the Hermit. All those are pretty close in age. So when you look at the Grand Canyon, you say there are limestones and there are shales and there are sandstones, and mudstones. And those are different kinds of rocks, and each one of those is deposited in a different kind of environment. The three limestones are the Muav down in the Cambrian section, the Red Wall in the kind of the middle of the canyon, and then the Kaibab, which forms the rim of the canyon. Each one of those limestones was deposited in open marine water. They have marine organisms like corals and things like that that can't really stand muddy water. So each of those three was deposited in fairly clear water. The Muav a little less clear, but still clear. And each one of those was deposited at a time when Arizona, this part of Grand Canyon, was near the equator. So the continents were moving around, going north and south of the equator, rotating, doing all the things that continents do attached to plates. But the curious thing in here is each time we were at the equator, we deposited limestones because we were in tropical environments that had clear, warm water, and so things like corals could thrive. So I'm standing on the Kaibab limestone, and you can see all across here, there's almost nothing on top of the Kaibab in here. Right after the Kaibab was deposited, there was another karst event. And so it got eroded down, and you deposited, you know, these angular pieces, and you dissolved a bunch of the limestone. That's happening to some extent as well on the modern land surface. So you're eroding that down. After this karst event that first formed right after the Kaibab was deposited, you deposited a series of red rocks, the Triassic Moenkopi Formation, but those rocks are totally stripped off of here. In addition to the Moenkopi, there were a whole bunch of other Mesozoic rocks on top, and they're all gone. They were all here, but they got eroded away. So I'm standing on the Kaibab. This rock is about 250 million years old, thereabouts, and it's got some marine fossils. I can actually see some of them in here. And this surface is pretty close to the surface that existed when the seas that deposited the Kaibab withdrew. And now that surface is back here at the surface, being eroded and weathered. We're in the eastern Grand Canyon, where you can see the three main sequences of rocks. Down in the inner part of the canyon, in the dark inner gorge, are the Precambrian metamorphic rocks and the granitic rocks. The metamorphic rocks are the dark rocks, and the granitic rocks are the pinkish layers and dikes, you know, little thin things like that. And then sitting on top of that is the second series of rocks, and you can see these tilted rocks. That is called the Grand Canyon Supergroup, and it has a number of formations in it, and groups in it actually, and which is why it's called a supergroup. And then the last sequence of rocks are the flatline Paleozoic layers. So you have the crystalline rocks in the inner gorge, you have these somewhat tilted Grand Canyon supergroup, and then you have the flatline Paleozoic rocks. The boundaries between these three different groups of rocks are really interesting in this perspective. At the bottom is the Precambrian crystalline rocks, and then you can see the lowest of the tilted Grand Canyon supergroup rocks sitting on top of it. It's kind of cream color with a little bit of green in it. And that contact is an unconformity. The rocks below are 1.75 billion years old, and the rocks above are about 1.1, 1.2 billion years old. And so there is about 500 million years of Earth history that's not represented at that boundary. It's an unconformity, so that means there was erosion in there and you beveled the underlying rocks. So if you look at the history in here, you say, okay, those rocks in the inner granite gorge, the metamorphic rocks, those were deposited on the seafloor. They got metamorphosed at 15, 20 kilometers, something like that. And so those rocks had to have 15 or 20 kilometers of material deposited on top of them. Then they got heated up, changed the minerals, that's what metamorphism is, and those rocks also got squeezed and folded so that now the layers are standing on end. You can't see that very well from here, but that's what they're doing. And then those rocks that were 20 kilometers had to get uplifted to the surface, and you had to erode 20 kilometers of rock off the top. And then once those rocks were at the surface, then you could have the seas come in, that lowest gray layer. It's a marine rock, it's limestone. And so you had to have the seas come in and deposit that lowest layer. But sedimentary rocks are generally deposited in nearly horizontal layering. And so that layer was sitting on top like that. Later, that layer had to get tilted. And then if you look at the contact at the upper part of the Grand Canyon supergroup, it's the flat-lying Paleozoic rocks on top. So you have the Grand Canyon supergroup like that, and you have the Paleozoic rocks like that. That contact between the Paleozoic rocks and the underlying Grand Canyon supergroup is another unconformity. And you'd call this an angular unconformity for sure, because of the way things are. If you look at the upper contact of the Grand Canyon supergroup, those rocks are tilted, but they have flat-lying Paleozoic rocks on top. And so that's another unconformity, an angular unconformity, because the rocks below are tilted. And the Paleozoic rocks just came across that beveled surface. So the history in here is, for the Grand Canyon supergroup, you deposited on the Precambrian crystalline basement, you tilted it, and then you beveled it, and then the first Paleozoic seas came across the top. That contact separates rocks that are 1.1, 1.2 billion years old from rocks that are 500 and something million years old above. So there's another 500 million years of time that's not represented along that unconformity. The thing that's really wonderful about Morin Point is the two unconformities merge. So you can see the lower unconformity between the crystalline basement and the Grand Canyon supergroup is like this, and then that gets beveled across by the unconformity at the base of the Paleozoics. So this way, that unconformity has 500 million, that unconformity have 500 million. Once that other unconformity, the upper unconformity bevels across it, now you have Cambrian rocks, 500 million years old, sitting on rocks that are 1.7, and so now that unconformity represents 1.2 billion years of Earth's history that's not recorded there. It's not like nothing else happened, but at this particular place, there's no record of what happened except we had to have erosion. One of the things that this relationship tells us is the uplift, the big uplift of the Precambrian basement rocks from 20 kilometers to the surface. That actually happened before the Grand Canyon supergroup time, because it's sitting on metamorphic rocks. And so the big uplift had to happen between 1.7 and 1.2, and you brought those rocks up to the surface, and then you deposited some thickness of layers, a kilometer or two thickness of layers on top of it, and then you tilted those layers and beveled it. But those rocks had already been uplifted to the surface most of the way. The other thing that Morin Point has that's really special is, as the Grand Canyon supergroup rocks got tilted, all those layers are not the same resistance to erosion. And so even today, some of them make cliffs and some of them make slopes. You can see there's a really nice cliff of one of the formations, Shinnemook Quartzite, and it's sitting on an underlying shale unit shown in red. And so those units today have this different expression, different response to erosion. A billion years ago, they had that same expression. And so in here, if you look across the canyon, you can see the basal Cambrian sandstone, the Tapeats, just goes away on that other side. And that's because this quartzite made an island and the Cambrian seas lapped out against it from several directions. And so we're seeing here an idea of what the landscape looked like 500 million years ago. That's what geologists, that's what we love about geology. You can come into a place like this and you can say, here's what it looked like X numbers of million years ago, in this case 550 million years ago. But so you can see the quartzite, it sticks up. So the seas came in, that deposited the Tapeats. At that point it was still an island. Later the seas got higher and you deposited the Bright Angel Shale, the second unit up in the Paleozoic, and the Bright Angel Shale is sitting on top of that rock. There are places that even the Bright Angel Shale didn't cover the islands, and so you had the Moave limestone finally cover that islands. And so it's this really interesting kind of cross-section of what the landscape looked like. And it goes along with what geologists say, the present is the key to the past. And so if this quartzite is more resistant to erosion today, under these conditions, it was probably the same, more resistant rock unit in whatever conditions existed 550 million years ago. A little closer to the edge, I don't want to stand over there, so I'm not going to show you from here. We'll take a picture of it. There's an example of this island right below us in here. This is a little place called Red Canyon, and it's got the same rocks. It's got the lower slope-forming red shales, and then it's got the cliff-forming tilted quartzite above it. And again, the Tapete sandstone just pinches out against that, and it's Bright Angel Shale sitting directly on the quartzite. So you can see that, and it's probably the same island, and also these rocks are tilted, and so this island was linear because it was following the strike, the trend of the units across the landscape. And so, and the thing that's amazing about this place is you can just see all this stuff, and if you kind of know how to think about it, you can figure it out. We're in the eastern Grand Canyon at Lippin Point, and behind me is a beautiful view of the unconformity between the tilted Unkar group below, which is part of the Grand Canyon supergroup, versus Cambrian sandstone flat-lying above. And so it's a beautiful angular unconformity. And so there are various units below the unconformity. There's red sandstones and siltstones. There's a dark layer that's basalt flows. And then there's another layer that has ledges and slopes. All of that stuff's tilted. And then there's a flat-lying ledge wrapping around the topography of the Cambrian Tapete sandstone. And so the contact between those two rocks is the great unconformity, at least one manifestation of it in here. The rocks below are 1.2 billion, the rocks above are 550 million, and so there's more than 500 million years of geologic history not represented at this place. Now it turns out that a little up canyon, you can see there's some gray slope-forming rocks on the right edge, and that's another group within the Grand Canyon supergroup. It's called the Chuar group, and it's a bunch of mostly slope-forming rocks, and definitely gray-colored as opposed to all these reds in here. And that rock is even younger than the Unkar group, so there's a little less time represented there along that great unconformity, but still quite a bit. When people look at the Grand Canyon, you often say, how did it form? And how it formed is at the bottom of the scene, you can see the Colorado River. The Colorado River is what carved this Grand Canyon. And it carved downward, and then the tributaries went sideways and widened the canyon, and then big rock falls and pieces, just coming off the cliffs helped widen the canyon. And so in here the canyon's fairly wide, and in the lower part of the canyon you can see it's kind of gentle and slope forming around the canyon, right around the river, as opposed to once you go into the crystalline rocks and it's a steep gorge. And so the people who do boat trips on the Grand Canyon call this Furnace Flats, because you can see there's no trees and it's low and it's hot, there's no shade, and so it's a pretty hot place to be. And it's basically just carved in and among the Unkar group, this middle part of the Unkar group. There are quite a few Native American ruins down in the canyon where they had granaries and things like that. And so that's another thing that people typically visit as they go along the river. Another question that comes up about the Grand Canyon is, how old is it? And it's another one of those things that for a long time people thought we knew the age of the Grand Canyon. And so people said, well, the Grand Canyon is less than 10 million or less than 6 million, and that's the end of the story. And so there was a broad consensus, everybody thought that, and then there was some new techniques that were developed that help you get at the uplift age of the rocks and how close the rocks were to the surface. And so people came in and started doing those types of studies, and one group thought that basically the data suggested that the Grand Canyon was actually quite old, maybe like 50 million years old. Now, it's not like there's a date that tells you it's 50. There was some modeling involved and things like that. And so, you know, it's a little more squishy about what we know because it involves models. But it highlighted that maybe there was a possibility in here that some part of the canyon was a little older. Way down canyon by Peach Springs, there was really nice geologic work that had been done a long time ago, 30, 40 years ago. It demonstrated that there were canyons that had been cut by rivers flowing opposite to the Grand Canyon, and that they had cut down to, you know, some lower level of the Paleozoic rock. So some amount of the canyon in there was actually carved before the rocks that filled those little canyons were deposited. And those rocks are 30, 40, 50 million years old. And so the idea is that some of that material, some of that canyon cutting happened quite a while ago. More recently, people came in and did some of these other new techniques and looked in here, and they said, well, we don't think it's as old as 50 in here, but we think this part of the canyon in here might have been carved at 15 to 20 million. And carved by either, not by the Colorado River, but maybe by the Little Colorado River or some other drainage that's flowing this way. And so there's a lot of evidence in here that the canyon has a complicated history, that it wasn't all carved at the same time. So today, I think most geologists agree that there's a multi-stage history of the Grand Canyon, and it was carved at different parts were carved at different times, but a lot of the recent canyon cutting is still less than 6 million years old. And so, you know, when you look at this, you have to realize how much material was removed here in the past 6 million years. And you might say, where'd that material go? The Colorado River goes down along the California-Arizona border, flows into Mexico and goes into the Gulf of California. And there's a huge thickness of sediments down there in the Gulf that's probably the material that came out of here. And at times, the river actually flowed into what's called the Imperial Valley, where the Salton Sea is. And there's a big thickness of sediment in there that's also clearly derived from up here. And so there's a lot of material here, and it got carried down canyon by the Colorado River at various times. And the river wasn't always this little. At times it was probably bigger when there was more rainfall, etc., melting glaciers, all that. And so you had a lot of erosion in here, and then you widen the canyon, and you eventually produce this grand spectacle that we see here. One of the other things that you can see from here is this is the North Rim. For starters, the North Rim is about 1,000 feet higher in elevation than the South Rim, where we are. And so those rocks have a gentle slope, gentle dip towards us in here. There's that, but then you can see in the far distance, the rocks look like they're tilted like that. And the cliff on the far right, which you probably can't see, is called the Palisades of the Desert. And that's also capped by Kaibab limestone. We're on Kaibab, that's Kaibab, that's Kaibab, but they're very different elevations. Between those two, there is a big monocline, a big fold that starts out flat, has a dip, one dip, monocline, and flattens out again. And this is called the East Kaibab monocline. And so it is this thing that uplifted the main part of Grand Canyon that makes Grand Canyon pretty deep, like a mile deep. Because once you cross the East Kaibab monocline, you're in Marble Canyon, and it's half the depth, something like that. And the difference between those is the amount of uplifting and down dropping along the East Kaibab monocline. On the backside of the Palisades of the Desert is the Painted Desert. And so you have the Mesozoic rocks, the Moenkopi and the Chinle, from here east for quite a ways, actually, nearly all the way to New Mexico. And so these rocks were down dropped like this, and so you preserve higher units in that down dropped block, whereas in this uplifted block, you stripped all those Mesozoic units off the top. And so you're now just left with the Kaibab at different elevations. One of the other things that people notice about the Grand Canyon is that the river is much closer to the South Rim than to the North Rim. And most of that is related to the dip of the rocks. So we're down here, so we're lower in elevation than up there. We get less rainfall, less precipitation, and so this cliff is probably eroding back a little slower than the cliffs up there. The other thing is up there you're like this, and the rocks are tilted a little bit towards us, and you're trying to peel stuff off, and it's a little easier to do that than to have this big cliff and you're trying to erode it back. So there's more precipitation. The dip of the rocks is involved a little bit, and then the river probably, because of the dip of the rocks, has probably migrated this way with time. But at some point it gets locked into its position and it's not moving anywhere. So right now that canyon's, maybe in another 5 million years it'll move a little bit more this way, but it's kind of stuck at this point. Another part of the Grand Canyon story that has a lot of discussion going on now is, how do you cut a canyon this big? Do you start with a river that's way out west and it cuts through some cliffs and it keeps cutting and cutting and cutting and come up here, and so you get this thing? Or did you have some kind of earlier canyons here, and then the Colorado kind of finds its way into this earlier canyon and then starts cutting like crazy? There's a third option. East of here, in what's now the Painted Desert, in the valley of the Little Colorado River, there are a series of lake beds that are about 8 million years old. And those lake beds accumulate up to a particular elevation, and that elevation is pretty close to being able to pour over some low spot in this wall of the canyon and pour into the Grand Canyon. So you could have had a lake that emptied into the Grand Canyon, and that either really started cutting the modern phase of canyon cutting in the Grand Canyon, or it accelerated what canyon cutting had been going on.